Everything seemed to confirm what I had been taught at the University of Florida. But one day I came across a book, and some of you here may know it. It's written by some people who are today creation scientists, and they were then creation scientists. It's called The Genesis Flood. Well, I was curious about everything, so I read the book, and in the part of the book, in the last part of the book, they mention a phenomenon called fluorochemical radioactive halos. These were mentioned because it was this phenomenon in the basement granite rocks of the world that supposedly determined whether or not one could actually ascertain dates or ages using radioactive dating. And as a physicist, of course, this was my main support for evolution. I believe that indeed one could, by radioactive dating, date the Earth to be several billion years old, and the fossils within the rocks were hundreds of millions of years old. But I began to realize that if one has a rock sample, such as this granite I'm holding in my hand, which presumably, on a uniformitarian basis, is several billion years old. Well, what happens if one tries to date this, or the process that one goes about in dating it? You take the rock in the laboratory, you crush it, and then you do some chemistry on it, and you extract elements like uranium, which is radioactive. Then you extract the daughter end product, which is lead, and you measure one and the other. And if the transformation rate of uranium, which is radioactive, is a constant over a period of time, over the time presumably the Earth has been here, then you can calculate the age of the rock. Now, the rock, of course, doesn't have any age stamped on it. We all know that. But I realized more fully than ever that everything really hinged on whether indeed that assumption, that constant decay rate assumption, was valid. And these tiny little halos that I had just found out about were supposedly the key that told scientists years and years ago that the radioactive decay process had been constant over what we call geological time. And as a result of that, I knew that this is where I wanted to begin to look again. Was the basic premise really true? Well, at this particular time, I had transferred operations from the University of Florida. Pardon me, I went to the defense industry, and then I got out of the defense industry and taught for a while, and then I went to a small college and taught for a while. Then I went to Georgia Tech. I began working on my PhD in physics in 1962. It was about this time my interest in the age of the Earth really began to focus. In fact, I was there to get my PhD and teaching at the same time. Well, I no sooner got on campus than I wanted to, of course, think about a thesis topic, and I'd become very interested in this topic of radioactive halos. I'd been doing some reading and studying for a few months. So in the fall of '62, I began to think very seriously about this as a thesis topic, and I went to see the department chairman to find out how he might feel. Well, I was a little bit surprised. First of all, he indicated to me that he himself had been a believer, or creationist, so to speak, years ago. He had accepted evolution, and he sort of warned me off the ground that I was about to tread on, saying that he didn't feel like, first of all, it was going to amount to anything for me to do any research in this area. And in every cordial way and kind way that he could, he tried to dissuade me over the next few months from actually wanting to do the topic, wanting to do thesis in this area. But as things have it, of course, I became more and more interested, and as a result of that, felt I had to look into this area simply to satisfy myself. I couldn't go on with a great deal of uncertainty in my life as I had at that particular time. So I told him this, and I stayed there for 2 years, but still conversing with him back and forth, and he finally got around to telling me that if I really felt that strongly about it, that I should not plan to stay and get my PhD at Georgia Tech, that indeed if I wanted to stay, it was going to have to be with another thesis topic. And he said, and whatever might happen, so what would happen to Georgia Tech, by the way, if you did find something that would call the conventional scientific view of Earth history into question? He said, you could be an embarrassment to this institution. And I said, well, I never thought of it like that, but I suppose that was a possibility. In any event, it became very clear that he did not want me to stay and to do that research. I wanted to do it, and so I voluntarily left. So in the summer now, this is 1964, I and infringe upon my wife's very good nature and began to do research on nothing, meaning no financial resources. I had borrowed a microscope, and I had some mineral samples that had halos in them. In fact, I took a trip to Dalhousie University, where this kind of research was done many, many years ago, in the 1930s. On borrowed money, for that matter, and began to use the borrowed microscope to look very carefully in the samples of rock that I had to try to find these special halos, meaning now special in this case, meaning simply the ordinary uranium halos, the halos that supposedly would tell me whether or not this decay rate had always been constant. So I put everything I had into trying to find the answer as I began this journey, which you're going to hear more about this evening. What did I find as I looked into these rocks? Well, the kind of rock that I used mostly was what we call biotite, a crystal of mica. And the reason I use this type of mineral mostly is because it's very easily cleaved. You can make a thin section, a very thin section of the rock itself by simply putting a piece of Scotch tape on it, peeling it back, putting it on a glass slide, putting it under the microscope, and begin to search for these little tiny radioactive halos. This time we'll go now to the 35 millimeter projector and we'll discuss, and I'll show you what I found over the years that I've been working. What you see, of course, is a little crystal of biotite inside the penny, which I've just shown you. This is the kind of mineral that I was working with. What you're seeing now is a uranium halo. What has happened is, if you look at the very tiny dot in the center of that series of rings, what you're looking at here is something that developed as a result of radioactive particles being emanated or shot out from the center, that little tiny center in the front, or in the middle of the halo itself. You see, I think, 5 separate rings. Now, that halo developed as a result of uranium-238 decaying sequentially, all the way down from uranium-238 to uranium-234 to thorium-230 to radium-226 to radon-222, and then it goes through a series of polonium isotopes, ends up in lead. It's two-dimensional as you're looking at it on the screen tonight, but in the rock it's three-dimensional. What I've done is to slice a section right through the center of the halo itself. Now, the reason scientists, geologists, physicists were interested in these halos is because the ring structure, the size of those rings, they thought, gave information as to whether or not the uranium decay chain or uranium itself had decayed at the same rate that it's decaying now. And that's the reason for that. The importance of that is that everything concerning, of course, the history of our Earth depends upon accepting the basic premise of uniformity, or what we call the overall principle of uniformitarian principle. Well, in looking at this particular sample, you might want to try to jiggle the connection down there. That might help a little bit. Otherwise, we'll just continue with letting you push the slides one by one. Here we have at least a schematic indicating to you what is happening in the mineral. As light interacts with photographic film to give you a picture, so tiny particles emitted from a very tiny center will discolor the mineral, at least if you have the right kind of mineral. It's a chemical reaction, and that chemical reaction produces a coloration in the mineral itself, just like light interacting on photographic film. And you can see the little arrows extending from the center. Those arrows denote the distance through which some of these particles will emanate or travel before they come to rest in the mineral. Now, you see, we've sliced it in such a way to make it appear that it's three-dimensional. In other words, you really have a sphere, and this is exactly the way it appears in the mineral itself. Most of you, perhaps, will not understand all that's involved in this particular diagram. What I'm showing here is the so-called uranium decay chain. It starts with uranium-238. If you look at the arrow going to the upper right, you'll see a little symbol, the Greek symbol alpha. That means that uranium-238, the nucleus emits an alpha particle, a rather heavy particle, and it decays to what is known as thorium-234. Then you see the arrow going down to the lower right. It's a beta particle. That particle is very light. It's an electron. It doesn't produce any coloration. So every time you look and see an alpha particle in that chain up there, you see a particle that conceivably can produce coloration or a ring. In other words, if you have, for example, a cannon, and you put a shell in the cannon of a certain specified powder load, the shell is going to travel the same distance each time, provided you have the same powder load and you're firing it through the same medium. Well, here is a cutaway or a schematic. If, again, the radioactivity is there in the center, then all these different parts of the uranium decay chain, all the different daughter products there, will give you rings or shells, colored shells, which develop around that little tiny center. You have to have now just not one or two, but you have to have about 100 million particles that will be produced in order for this coloration to develop.